cross a point on a link, as the number of vehicles increase, you get more and more delay is the cost function that is usually used. But the reality is kind of interesting. If you look at the traffic flow relations that's out there, what you'll actually find is that there are two regimes out there. You do have the situation where there are only very few vehicles out there, and you have a pretty high speed of all the vehicles. So you end up getting a high speed, low flow type of condition here. Okay, that corresponds to low flow, meaning low travel time. Then you get this, the second part of the flow curve, which is a congested situation where there are a lot of vehicles on the road, but they're not moving. If there are a lot of vehicles, like the Bangkok situation that I was talking about that I saw this morning, there are a lot of vehicles on the road. If nobody is moving, then the number of vehicles crossing a point is very low. But that's a condition where you have low flow on a network link associated with which there is a very high travel time. So in other words, this travel time curve actually goes back and goes up to infinity. All right? But that's not what is assumed in our standard planning models. And standard planning models will say as flow increases, this travel time will go up to infinity. But that's not the actual flow curve. What is interesting about I like to present this curve in as many occasions as I can, because I really consider this as the dirty secret in transportation modeling that people don't want to talk about. In fact, several years back, and Professor Anthony Chen will remember this, this is basically what got Professor Chen's PhD work going at UC Irvine in the mid-90s when he was doing the research. And we found that this is hardly ever discussed in any of the literature, and until we actually wrote a paper from Anthony's dissertation at that time, and we put these curves out there. And we said, well, this is the problem. We need to talk about this. I don't know what has caused this to be much less appreciated by the transportation planning community than it should be, but that's a fact. So let me not spend a lot more time on it, but you see the basic problem in the planning models, and hopefully you'll hear more about it in this workshop. But this has got some effect in emissions analysis, though. If you're talking about how much flow is there in the network, you may be able to get away with it, and there are some reasons for that. But if you're trying to predict emissions in a network, especially from trucks and industrial freight movement, etc., your problem is that a lot of the emissions happen in this condition that I was talking about with low flow and low speed and very high travel time at low flow. Okay, does this happen in a network? Let me again give you an example from the Los Angeles freeway. This is taken out of the of a system that was developed by the California Department of Transportation called PEMS, Performance Measurement System, where you have the detectors on the freeways and all the data is coming into one place, and you can actually pull out the data. This is what actually happens on a freeway where between 2 o'clock in the afternoon all the way to 8 o'clock in the afternoon, we were seeing flows as low as 300, 400 vehicles per hour per lane. That means nobody's moving. So you're getting hardly any throughput on the freeway. This is that very high density, low flow, high travel time condition, the Bangkok condition, if you want to think about it that way. That happens almost 6-7 hours on a freeway. And what happens in this condition is that every truck that is going through that network is stopping and moving and emitting 10 times as much emissions. This is an important problem that needs to be kept in mind, and it's particularly applicable for Thailand in my mind. Okay, so an evaluation framework for it, and I already mentioned, is to do a microscopic analysis, do a separate analysis of the emissions using detailed vehicle movements and trajectories. And from that emissions, we also had in our work, as if you remember the map that I showed, there was also a rail link in that Alameda corridor. And so there was this question of how much of freight can move between the freeway and the rail link, and can we do some management of the freight movement on truck versus rail. So we actually had a modeling of the rail yard movements, and that requires a totally different simulation scheme. I'm not going to get into the details of it, but diesel train engines also emit a lot of emissions. So any study on how much should be moved between rail and trucking, and that has to be done also with a modeling of the rail yard emissions. So a few scenarios we looked at, and mainly the Clean Truck and Clean Locomotive program that was instituted a few years back actually, but by 2010, all of the trucks were expected to be adhering to certain standards of emissions, as well as the locomotives running on those rail yards. They also needed to be Tier 2 locomotive, Tier 3 locomotives actually. And then look at the model shift from truck to rail. That's what the framework was meant for. What does it entail as far as our analysis is concerned? You end up with this is the Los Angeles area that you're seeing. There are 5 different counties at almost half of the population in California lives in this area, and California is the most populous state in the United States. So you can imagine how large that network is. A portion of it here, if you can see the cursor, that is where the 2 ports are, and a network connected to that is what we are using for the modeling. So that network ends up becoming a set of freeways and a few arterials near the port, and we have made this network slightly bigger now, and I'll show that in a minute. And then you do the detailed traffic simulation in terms of every intersection, intersection's signal timings out there, every freeway entry point, the ramp control that is there to let vehicles onto the freeway. All of those details have to be coded, and every detector that measures traffic for the control, you have to set up those detectors in your computer model. So it's a extremely elaborate topic. About 3-4 PhD students lost a lot of their sleep over this. And this is where we start with. It's what is known as the static planning model. In this case, it comes from SCAG, which is the Metropolitan Operation Agency or Planning Agency, the Association of Governments, Southern California Association of Governments planning model. Well, thank you. Usually we get a note like this which says you have 2.5 minutes to finish. This one says you have till 10:15. Well, I have more time, which is very nice, pleasant surprise. Thank you. So from there, what happens is a model that in this case we made our microscopic simulation in a software called Transmodeler. If those of you who have looked into detailed microscopic simulation models, there are about 4 or 5 models which are popularly used around the world. One is Paramix, that comes from the UK, from Scotland, and a model called Aimson that comes from Spain. There is a model called Vissim that comes from Germany, and Corsim, which is the original granddaddy of all these models that came from the United States, that's not as used anymore. And the most recent, and perhaps in my mind, at least conceptually, one of the better software models that comes from Caliper Corporation from the US again, and that is the Transmodeler. It operates with the planning model of TransCAD that's used around the world again. So that's the microsimulation model that we used for coding up this network. And again, the port is at the bottom end, and you can see the freeways that go all the way to a whole set of rail yards that are there in various locations out here. And in fact, one of the things that we wanted to look at was whether the locations of these rail yards, if we make some changes, now remember, relocating a rail yard or even changing the characteristics of a rail yard, it's not an easy job, because these are in the middle of industrial areas, and there is tremendous investment needed to do those kind of things. However, if you actually see significant, public health costs, etc., that comes out of freight traffic on the freeways, and if we could move some of that to rail, and if the relocation of rail yards could help, that was a good thing. So we looked we wanted to look at some of these kind of details, which was all inbuilt in the complete framework that that I'm talking about. And again, to think about how difficult it is to code up a network for microscopic modeling. If you can imagine, in that network that I just showed, 1,500 similar intersections, and here there is 5 streets coming into one place. You have to actually physically spend 2, 3, 4 minutes for every one of these connections to be set in place. Which lane moves to which other lane? Where are the detectors placed? What are the signal timings? It takes tremendous amount of time. Maybe every intersection might take you an hour or two to code up. So you're talking about 2,000, 3,000, 4,000 hours of work to set up the signal details of a network. Is it worth it? It turns out it is. It's work that is well worth spending. And how do we estimate the vehicle emissions? Again, it's based on individual vehicles, link speed, and VMT. So what happens is, as the micro-simulation runs, we output how every vehicle moved in the network in every split second. You're talking about 0.1 second type of resolution in the simulation models. So with complete trajectories of vehicles, you know how every vehicle accelerated, decelerated at any point in time. And that gives us all the data that you need for a complete prediction of how much emissions will be coming from there. Again, this is not exact science. The emission models that are out there, even with the complete data like this, are still iffy. There are questionable aspects to these emission models. But this is the best that we can do because there is a wide variety of characteristics to vehicles. All it takes is whether a Honda Accord is from 6 years back or last year. Their emissions are different. So you have to make assumptions in some of these things, but again, you're doing much better than using the planning model and saying on the basis of an average speed for a link, which is already wrong, you can predict the emissions, which is absolutely a ridiculous way to do it. But that's all we so far had, unless you want to take trouble of the kind that I'm talking about, which is worth it. You may have to do it. And then you have this issue that I talked about. What is the mix of vehicle ages that is in a network? That becomes important. And again, remember, if you're thinking about, say, doing something like this in Thailand, you'll have to then consider developing additional models for the tuk-tuk or the little vehicles which are out there, which are big emitters of particulate matter out there. And I know that from some of the studies that were done in India, where we also have this, what they are called auto rickshaws. 3 people sit on it, and they run off a little scooter engine. And you used to have diesel for those, or petrol with a mix of kerosene with it, and it's black soot coming out of the tailpipes. One of them can do as much damage as 35 Honda Accords. So now, how do we model something like this? Takes work is the answer to it. So we went to get the details of something like this. As our focus was on trucks, we actually went to the truck registry. There is something called drayage truck registry. Now, drayage trucks are basically the flatbed trucks that are out there, which just simply take containers on it. So the word drayage just stands for that. So there's a drayage truck registry that comes from the San Pedro Bay Port complex, and we looked at the sort of the distribution, yearly distribution of trucks. And in fact, what you see at the end is a different distribution that happened after the clean truck program was formulated out there. And I don't want to go over all of the numbers, but here are some details that came out of maybe a year and a half of a couple of PhD students' sleep was lost. These are actual emission figures for the network, and I'll show a few more of details on it, including how much of reductions happened because of the clean truck program compared to the 2005 level. So, of course, there is no, remember, all of this work is needed because you don't have a way to monitor actual emissions by keeping some measuring device out in the field, which is never done. You cannot do that. So what all you can do is to go back and model, computer simulate what happened in 2005 with a different mix of vehicles out there, and taking all of the details of how the network was in 2005, and then you do the same simulation for 2010 and see how much difference would be there from the clean truck program. And significant reductions were found in carbon monoxide, hydrocarbons, NOx levels, particulate matter, and that itself, there are different standards. If you go to things like Kyoto Protocol, I don't know if any of you have spent time looking into the details of these things. There are a lot of specifications out there on different types of particulate matters and the allowable limits of those things. So PM 2.5 and PM 10 are two different types of particulate matters. All of them seem to reduce significantly. I don't want to spend a lot of time on this mainly because I don't know much about this topic, which on the rail emissions part, which is a separate model. And this was actually the PhD research of Dr. Mana Sankapichai, a student actually from Thailand that we had at UC Irvine. He's now a modeler at SCAG, the Southern California Association of Governments Planning Organization. He did a very elaborate modeling of the rail network as well as the different yards which are nearby in various locations. You can see the rail line going up and ending up in the commerce yard, for instance. So there are 7 different significant rail yards where all the shunting operations of rail locomotives to move these containers around in the yards, that caused a significant amount of emission. So this was actually modeled separately for the rail yard also. Again, details of it from Mana's dissertation, just for you to know that these are very detailed numbers on emissions that we ended up finding for each of the rail yards in that whole industrial area that you saw. And this, again, to give you a sense of the details, there's separate cargo handling equipment that are there in a rail yard, bulldozers, cranes, forklifts, line haul, switchers. These are the shunting services of the locomotives inside the rail yard. These are all modeled separately, for their numbers. Microscopic simulation again. Okay. Next important topic is the air dispersion analysis, which goes to CalMet and CalPuff, which are the latest 2 software that are developed in the US for meteorological data processing. That's the CalMet, and the actual emission dispersion. So the first part is really looking at specifying what type of a day you want to model. There is wide disparity in emissions that will happen on a cold day versus a hot day versus a windy day. So the CalMet part of the modeling is looking at, for the area that you are modeling, how many days of what type of conditions exist out there. And the CalPuff is an area-wide modeling of the wind patterns and the dispersion of the emissions that come from it. So in our case, we picked about 4 different seasons. Rain doesn't really happen in California much, so rain effects are negligible. It rains over like 3 days or something with a lot of water, and that's it. It never rains in Southern California is a famous song that's out there. which is ill-stated, but still rain is not a big issue, but it is an issue in a place like Thailand, for instance, if you look at the effect of rain. It's